Okay, so we're estimating instantaneous rates of change, and we're going to use a difference quotient. This is your difference quotient, this formula here. Okay, so change in y over change in x. In other words, the slope at a specific point is this equation here. So you have to eventually memorize it. Okay, and what it's talking about, we'll bring up a graph, and when they talk about instantaneous rate of change, oopsie, not what I was looking for. There you go. Nope. Thank you. Okay, so instantaneous rate of change. Cube. So actually this function is going to look like this. It's going to go like this. Okay, here's their function. And what they mean by instantaneous is, we'll go right in. Remember, we're doing average rate of change, so we find 2 points. Well, they're actually looking for essentially the slope at a specific value. Okay, and in this case, they were looking at 5, which didn't fall in our graph, but let's just say we're looking at, I don't know, right here at 1. Okay, we're trying to find a slope at 1. Well, what they're looking for is a line that's actually considered tangent to this. Okay, so do you see it doesn't cross through, it just touches and goes away. And that's called a tangent line. So we're looking for the slope at that exact point. That's this point here. Well, to find that, this is what we do. Our A value is the point in time we're looking for. And in this case, they asked us for when it was at 5. I think that was the question. So find out the volume at 5 seconds. Okay. So A in this case is our 5. That's what our point is. H is an extremely small value. That's what it stands for. An extremely small value. Okay. And essentially what it's saying is you could put in, for average rate of change, you could put in like 0.001, you know, and make it 2 points when we're talking about average rate of change. But using this different quotient, we'll actually be able to eliminate h. Okay? So what this is whatever the function is, we put in 5 plus h into that equation. And then we subtract it from the function at 5. So in other words, here's our coordinate at 5. And here's our coordinate that's a little bit past 5, just a very, very small point. That's what h stands for, a very small amount past that exact value. So our function in this case was volume. And it said the function f at x was equal to x cubed. This was how our volume was increasing. So f at a plus h, which is essentially our x, a plus h, is equal to, and in this case, our a value is 5, right? So I'm going to replace a with 5. So I'm looking for a function 5 plus h. So I plug it into this. I replace my x value, right? Because here's the x. Well, I replace x with 5 plus h. So now we have 5 plus h cubed. That's what this first function is, right here. Okay? 5 plus h cubed. And then our other one is f at, well, the value of a. A we know is 5 in this one. So in this case, the other function we look for is f at 5. Well, that's just simply 5 cubed. Well, that's 125. So that was easy to find. Okay? So I can start to plug it into my equation. Our different quotient, the change in y over the change in x, is equal to our value of 5 plus h cubed minus 125 divided by h. And you might say, where did I get all this? Well, what that was, remember again, that was our f at a plus h, that's what this equation stands for, minus f at a divided by h. And I'll highlight them to show you. F at a plus h was what we solved up here. That's what that value is. F at a was when the function was 5. Well, we discovered it was 25. And we just still have the h there. So now what we're going to do is simplify that equation. Okay? So let's bring it down here. To simplify it, we have 5 plus h times 5 plus h times 5 plus h. It's a cubed function. That's a bit annoying. Minus 125. Oh, we might have to factor this using cubes. This could take a while. We'll expand. Okay. When we go to solve this, we do one bracket at a time. So we distribute. 5 times 5 is 25. 5 times h is 5h plus 5 times h is 5h, so it's actually going to be 10h. And h times h is h squared. and then we still have to multiply it by the other one. Okay?
Mm-hmm.
Does this make sense so far?
Kind of.
I did distributive property. I did 5 times 5, 5 times h times 5, h.
Yeah, that makes sense, but just like up to this point, kind of confusing.
Kind of confusing. The difference quotient's the tough part. Okay? Then again, 25 times 5 gives us 125. 25 times h is 25h. 10h times 5 is 50h. Oh, no, that's 25h. 10h times h is 10h squared. And h squared times 5 is 5h squared. H squared times h is h cubed. And then minus 125. So a lot of expanding I've done. Okay? Just because it was a cubic function, which you guys would have worked with last year. And now we collect our like terms. Well, positive 125 and negative 125, I'm going to make a 0. Okay, so we know that like term's gone. H cubed has no like terms. With h cubed, we also had what? Squared, 10h plus 5h. So that's going to give us 15h squared. Right? Mm-hmm. And our other value, 50h plus 25h, is going to give us 75h, right? Mm-hmm. 75h divided by h. Well, I can factor an h out. The goal is to factor out the bottom term here. Mm-hmm. This h. We always want to get rid of it. Well, luckily, there's an h in all of these, so let's factor h out of this. Common factoring. Do you remember that? So we take h out, and we're left with h squared plus 15h plus 75. Well, that allows us to get rid of our fraction, because now these h's divide to make a 1. So I'm left with a function that says h squared plus 15h plus 75. And now what I would do is factor this. I'd factor this to find a proper value. Factors that make 75. What two terms add to 15 and make 75? Positive 75. You might have to use quadratic formula. Solve something like that. 5 divided by 5 gives us what? That's not good. 3, that's not good. Yeah, we might have to find quadratic formula. So, let's see what they actually end up getting in the end here. It's cubed. Oh, they used an extremely small value. So we did the calculus way. We would factor this, and in the end, they'd find a factor of h, after you factor all this, of roughly 74-ish or 75-ish. It's like 74.85, something like that, when you factor this all out using quadratic formula. So what that's saying is we could say approximately 75. So the instantaneous rate of change here is it's increasing by 75 cubic centimeters at 5 seconds. Okay. The idea of this is just that h stands for really small amount. So you could think of it like we took 5. This is essentially a slope formula, and we took 5.0001, and we found the value here and subtracted from our value of 5, and then we divided by the difference between those two. We can create this formula, though it can be a bit confusing when I create it. Your teacher will probably talk about this with you. This is also a method they use in calculus. So if you do start to understand this in order to solve it, it can be very helpful because you're going to use it in calculus too. Okay? Just look it over. They might not ask you to use it that one, but it is a way to find instantaneous rate of change.